Ready for a deep dive. Today, we're tackling a paper from a young Albert Einstein.
Oh, wow, Einstein.
Yeah, before the whole relativity thing.
So early Einstein.
Super early Einstein. This one's all about Brownian motion.
Brownian motion, huh?
You know that kind of jittery motion you see, like dust particles in the air?
Yeah, I've seen that.
Or like little bits of stuff in water.
Right, they just kind of bounce around.
Exactly. Seems random, right?
Well, I always wondered what caused that.
Me too. And that's what's so cool about this paper. Einstein used this seemingly simple thing to tackle a huge scientific debate happening at the time, the existence of atoms and molecules.
Whoa, hold on. They were still debating that back then.
I know, right? It's crazy to think about it now.
Yeah, it seems so fundamental.
Totally. So our mission today is to figure out how Einstein connected this tiny jiggling motion.
The Brownian motion.
Yeah, exactly. How he connected that to these big ideas like heat and thermodynamics.
The building blocks of the universe.
Exactly. All that from just watching tiny particles move around.
Pretty amazing.
Now, to really get this, we need to understand what science was like back then.
Okay, take me back in time.
So picture this. Scientists are wrestling with concepts like osmotic pressure.
Osmotic pressure, huh? That rings a bell.
But they didn't have the tools to really explain it at the molecular level.
Okay, now I'm a little lost. Osmotic pressure. What's that in simple terms?
Okay, great question. Think of a balloon, right?
Okay, I'm with you.
When you blow it up, the pressure inside builds up.
Yeah, because of the air you're putting in.
Exactly. Now, osmotic pressure is similar, but instead of air, it's water molecules trying to balance out their concentration across a membrane.
Okay, like trying to even things out.
Exactly. So imagine you have salt water on one side
Okay.
and pure water on the other, separated by a membrane that only lets water through.
Like a filter.
Exactly. The water molecules rush towards the saltwater side to dilute it.
To make it less salty.
Right, and that movement creates pressure.
Okay, so that's osmotic pressure.
You got it. Scientists knew it existed, but they couldn't explain the how, the why.
The mechanics of it all.
Exactly. And this is where Einstein comes in.
Okay, what did you do?
He started with a simple yet bold assumption.
Let me guess. Atoms and molecules are real.
Bingo. He said, what if molecules exist and they're constantly bumping around?
At a time when that was still a hot debate.
Yeah, that was a gutsy move.
And I'm guessing that gutsy move paid off.
Oh, it did. But he didn't stop at just the idea.
He had to prove it.
He did. He used a new approach called statistical mechanics.
Statistical mechanics, huh?
Yeah, it's about looking at the big picture, the overall behavior of a system.
Not just tracking each individual piece.
Exactly. And through this, he linked that random jiggling motion.
Brownian motion.
Yeah, he linked that to the invisible world of molecules.
So he's saying if we assume those molecules are constantly bumping into bigger particles, that would create the jiggling we see.
Exactly. And he didn't just stop at the idea. He went further and derived a mathematical formula.
A formula.
Yeah, to calculate the mean displacement of a particle over time.
So he actually put numbers to this seemingly random dance.
He did, and that was huge. It created a direct link between what we can observe,
The jiggly.
yeah, and the invisible world of those tiny molecules.
Incredible. So he's not just speculating, he's quantifying it.
Exactly, and that's a key difference, right?
Huge difference. It's not just a theory anymore.
He even gave a specific example. He calculated that a tiny particle,
How tiny are we talking?
0.001 millimeters in diameter,
Wow, that's tiny.
right, suspended in water, would move about 6 microns in 1 minute.
So he's saying if you look under a microscope, you should see this.
Exactly. He was making a testable prediction.
Classic science.
Classic. And it was this testability that led to the eventual acceptance of the atomic theory.
Because they could actually test it and see it.
Exactly. He gave scientists a way to indirectly see atoms.
By watching their effects on the bigger particles.
Mind-blowing, right?
Totally. So Einstein's paper, it's not just about Brownian motion.
No, it's about so much more.
It's about the very foundation of matter.
And it all started from these tiny jiggling particles.
Amazing.
But hold on, there's more.
Oh, there's always more with Einstein.
This paper goes beyond Brownian motion. He used this to tackle osmotic pressure, too.
Right. We talked about that earlier, the balloon analogy.
Exactly. But how did he connect the dots? How did he use this new understanding of molecular motion?
To explain osmotic pressure in a way that made sense.
Yeah, in a way that went beyond what they knew back then.
Okay, I'm all ears.
So remember that membrane?
The one that only lets water through?
Yeah, and the saltwater solution. Well, Einstein took it a step further with a thought experiment.
Okay, love a good thought experiment.
He imagined a volume of liquid enclosed by that same membrane, and he argued that those suspended particles,
The ones that are too big to pass through.
yes, those exert pressure on the wall, just like the dissolved molecules.
Oh, interesting. So both the big and the small are contributing to the pressure.
Exactly. He was expanding the understanding of osmotic pressure to include these larger particles.
Because they're also constantly bumping around.
Precisely. It's like he revealed a hidden order behind the chaos.
It's beautiful, isn't it? How everything connects.
It really is. But how did he connect all these ideas? Brownian motion, osmotic pressure, molecular motion.
It all comes down to statistical mechanics.
Right, that big picture thinking.
Instead of tracking every single molecule, he used probability and statistics.
Ah, so he could describe the overall behavior without getting lost in the details.
Exactly. It's brilliant, really.
It really is. He bridged the gap between the microscopic and the macroscopic world.
And revolutionized our understanding of matter and heat.
Speaking of understanding, I gotta ask.
What's that?
Did Einstein actually call it Brownian motion in this paper?
That's a good question. You know, he didn't actually use that term.
Really?
Yeah, he called it the movement of small particles suspended in stationary liquids.
So where did the term Brownian motion come from?
It came later, named after Robert Brown.
Oh, the botanist who saw it first with pollen and water.
Exactly. Back in 1827. So, Brown made the observation.
But Einstein cracked the code?
He connected it to the bigger picture of the molecular-kinetic theory of heat.
Talk about a scientific revolution.
It really changed how we understand the world.
It's incredible how one paper can have such an impact.
It's like a domino effect. One idea leads to another and another.
And Einstein's paper is one of those first dominoes.
One that had a ripple effect across science and beyond.
It really highlights the beauty of science, how it's all interconnected.
And it all comes back to that curiosity, that desire to understand.
The drive to ask why.
And to see the order in what seems like chaos.
And to think all of this is laid out in a paper published over a century ago.
The brilliance of Einstein.
It's a reminder that great ideas transcend time.
Absolutely. And you know what? This is just the beginning. We've just scratched the surface of this paper.
There's so much more to uncover.
So much more. Buckle up, because we're diving even deeper.
Now let's get back to that formula Einstein derived.
The key to the whole thing.
The mean displacement of a particle. That's where he really connects the dots.
Between that random jiggling and the unseen molecular forces.
Exactly. But let's take a breather here, give everyone a chance to process.
Good idea.
We'll be back soon to break down that formula and explore even more of Einstein's genius.
Can't wait.
Back again for more Einstein. So last time we got to the point where Einstein wasn't just explaining why those particles jiggle, he wanted to calculate how they move.
Right, and that's where this formula for mean displacement comes in.
Okay, so let's break this down a bit. Feels like we're about to get into some serious math here.
It's actually pretty straightforward, the elegance of it all.
Okay, I'm all ears.
Well, what Einstein did was consider the forces acting on that suspended particle.
Okay, so we have our particle just hanging out in the liquid.
Exactly, and it's being bombarded by all these molecules.
A constant molecular mosh pit.
Huh. That's a great analogy.
That's what's causing this jiggling we see, the Brownian motion.
But there's another force at play here. Friction.
Okay, right. So the liquid itself is going to resist that motion.
Exactly. It's slowing the particle down.
So it's a constant push and pull.
A delicate balance. And Einstein brilliantly balanced those forces.
Okay, how did he do that?
Statistical mechanics for the random collisions.
Okay.
And fluid dynamics for the friction.
So he combined different areas of physics.
Exactly. And from that balance, he arrives at an equation that describes how far, on average, a particle will move over time.
So that's the mean displacement?
That's it.
But why mean squared displacement? Why not just mean displacement?
Oh, that's a great question. It all goes back to the nature of that jiggling motion.
Okay, so those particles aren't moving in straight lines.
Exactly. They're bouncing all over the place.
Up, down, left, right, all directions.
Exactly. So squaring the displacement accounts for that random multi-directional movement.
Okay, I'm with you. The longer the particle's out there bouncing around, the greater the average displacement.
The more it can wander.
Now, what about this diffusion coefficient?
Ah, yes, the diffusion coefficient. Think of it as a measure of how easily a particle can move through the liquid.
So, like, how much resistance it encounters?
Exactly. A large diffusion coefficient means less resistance. The particle can travel farther.
So it's kind of like swimming in water versus swimming in honey.
Perfect analogy. You'll go much farther in water.
Much less resistance.
Exactly. So the diffusion coefficient depends on things like the thickness of the liquid.
The honey versus water situation.
Right. But also the size of the particle itself.
So a bigger particle is going to have a harder time moving around.
Exactly. More resistance, smaller diffusion coefficient. And what's amazing is that Einstein's formula neatly connects all of this.
Wait, so he's connecting the macroscopic, how far a particle travels?
With a microscopic, the viscosity of the liquid, the size of the particle.
Okay, that is pretty neat. But did Einstein stop there? Or did he actually use this formula to do something?
Oh, he took it a step further. Always got to test the theory, right?
That's the heart of science.
Exactly. So he applies this formula to a specific case, a tiny particle, 0.0001 millimeters in diameter, in water.
Seriously tiny. What did he find?
He calculated that this particle, on average, would move about 6 microns in 1 minute.
So he could predict exactly how far this thing would jiggle.
Well, on average.
But still, that's some serious predictive power.
It is. And that's what's so crucial here. Einstein wasn't just making qualitative statements about Brownian motion.
He was making quantitative, testable predictions.
Exactly. And guess what?
They tested it and it worked.
Later experiments confirmed his calculations, and with remarkable accuracy.
So he not only explained Brownian motion, he provided a way to test his theory.
Right.
And they proved him right.
It was a huge win for the atomic theory.
Like he was handing them a microscope to see this invisible world.
But a microscope that used the dance of particles to see it.
That's incredible.
And it's just the beginning. This paper went on to have a huge impact on science, on how we understand the universe.
Okay, we got to dive into those impacts next time. This is already blowing my mind.
It's a lot to process, I know.
So we'll pause here and let everyone soak it all in. We'll be back soon to explore more of Einstein's genius. And we're back. More Einstein, more Brownian motion. It's wild to think how this one paper went on to influence so much of science.
Yeah, it's like throwing a pebble in a pond.
All those ripples spreading out.
Exactly. So where do we want to pick up?
Well, last time we focused on how this work really helped solidify the atomic theory, like atoms are definitely real, folks.
Yeah, Einstein put an end to that debate, but that was just one ripple.
Okay, so what other ripples did this paper create?
Well, think back to what Einstein was doing here. He was looking at tons and tons of molecules colliding, all those tiny collisions with bigger particles, and not just tracking individual molecules.
Right, he was looking at the big picture.
Exactly. The overall effect, that's the heart of statistical mechanics.
Ah, so he was contributing to this whole new way of thinking about physics.
Oh, absolutely. He showed how you can use stats, probability,
to bridge the gap between the tiny world of molecules and the things we actually see and experience.
like the jiggling of those particles.
Exactly. And that, my friend, is huge for thermodynamics.
Thermodynamics, the study of heat and energy.
Yeah. So we're talking about the fundamental laws that govern energy in our universe.
Pretty big stuff, right?
Yeah. But, hold on. There's even more, right?
Oh, definitely. Einstein's work went even deeper, challenging some really fundamental assumptions in physics.
Okay, like what?
So up until then, thanks to Newton, we thought of the universe as like a giant clock.
Yeah, predictable, everything neatly determined.
Exactly. But then along comes Einstein, and those jiggling particles and those random collisions.
And suddenly the universe isn't so predictable anymore?
Well, it's not that the laws of physics are wrong, but even if we knew every law perfectly.
We still couldn't predict everything.
Right, because at the most basic level, there's this element of chance.
Whoa, okay, hold on. So randomness is built into the fabric of reality.
It seems so.
Mind-blowing. That's a pretty radical shift in thinking.
It was. This paper chipped away at that deterministic view.
And opened the door to new ways of understanding the universe.
Like quantum mechanics, where probability reigns supreme.
Wow. So this seemingly simple paper about random motion
Ended up changing our entire view of reality.
amazing. It really highlights how interconnected science is, you know.
Oh yeah, everything's connected. One discovery can have massive implications.
Like a chain reaction.
Exactly. And, you know, at the end of the day, it all comes back to curiosity.
That drive to understand, to figure things out.
Exactly. Einstein wasn't just crunching numbers.
He was driven by this deep desire to know how the universe works.
To peel back the layers of reality.
And that's something we can all learn from.
Absolutely. It's that curiosity, that passion for exploration.
That leads to new discoveries, to new ways of seeing the world.
So let's keep those minds curious and those imaginations firing.
Yeah, there's still so much out there to discover.
The universe is full of mysteries.
And who knows what incredible insights are just waiting to be uncovered. So until next time, keep exploring, keep questioning, and keep that spark of wonder alive.